So let's look at some of the trig functions other than sine and cosine. So we're going to start with tangent. Y equals tangent x, the parent function. So the period for tangent is pi. The center, which we'll see on the graph, is at x equals 0. So let's look at the graph of the parent function. So tangent has asymptotes. My dashed pencil line won't show up, so I'm going to draw the asymptotes in red. So I'm going to put my scale here, and I'm going to let this be 0 in the horizontal direction. And my asymptotes for tangent are at positive pi over 2 and negative pi over 2. And again, I'm going to draw these asymptotes in red so you can see them. So those are the asymptotes. And tangent has this center inflection point here at 0, 0. And it has this pinwheel twist shape. This is what tangent looks like. So tangent looks like that. And as any trig function, it keeps repeating. If you found the values around the unit circle, it would keep going around and around and around. So every horizontal distance of pi, we get a repeat of the same function to the left and to the right. So we get repeats of these over and over and over. And these asymptotes, they're vertical asymptotes. Functions never cross vertical asymptotes. So the function's undefined on all of these asymptotes. So that's the graph of the parent function tangent. Now let's fill in some information for the case where there's transformations. So we could have any of these transformations, A tangent B x minus C plus D, but our book doesn't give us any vertical transformation, so I'm not going to put that in here. Now, amplitude doesn't really apply to tangent because it keeps going up forever to infinity. So A, we're going to revert back to what a transformation means in general, is a vertical stretch or shrink. Because the period of tangent is pi, the period of a transformed tangent function is pi over b, same b here. And asymptotes, so right now they're at positive pi over 2, negative pi over 2, and then they repeat every horizontal distance of pi. So to find a pair of asymptotes, you're going to start, oh, sorry, back up. C is a horizontal shift. So your asymptotes, if you think about starting at C, they are that C transformation, this one's not transformed, plus half of the period. And then so to the left, so minus half of the period. So I get 1 plus the period over 2 and 1 minus the period over 2. So let's do an example. So what if I have y equals 1/2 tangent 2 x minus pi over 6. So a bunch of transformations. So for A, have to think, did it reflect? Because if it was negative, it would reflect. And in this case, no. So it's a vertical shrink by 1/2. So it's going to look like we compressed it this way. All right. And C is pi over 6, opposite sign of this. So that's going to be to the right. So that means my center, this center of the pinwheel, moved to the right a distance of pi over 6. And since B is 2, my period is going to be pi over 2. So when I'm ready to do my asymptotes, I'm going to start at my center, my C, which is pi over 6, and I'm going to add the period divided by 2, which is pi over 4. So pi over 4, I'm going to subtract it as well, but I'll do this first. So common denominator, so 2 pi over 12 plus 3 pi over 12. So that's 5 pi over 12. And then I'm going to do this one shorter. So pi over 6 minus pi over 4. If you found the common denominator and subtract it, you find out that it's negative pi over 12. So now let's just put all this information on the graph. So I have an asymptote at negative pi over 12 and another one at positive 5 pi over 12. So I've got to decide how I'm going to label things here. So if I put my 0 somewhere, I'll put my 0 here. And I need multiples of pi over 12 on here because I'm landing on multiples of pi over 12. And I don't want to run out of space. So I'm going to make halfway between the dark lines the multiples of pi over 12. So if I make this negative pi over 12, this would be 0. This would be pi over 12. This would be 2 pi over 12. This would be 3 pi over 12. This would be 4 pi over 12. And this would be 5 pi over 12. And I'm going to draw my asymptotes in red just so that they're visible. So those are my asymptotes. So now let's put my C on here. So C happened at pi over 6. So right there, and it should be exactly in the middle between my two asymptotes, which is, and I know it's going to go like this. So now I just have to think, what did this 2 do to the function? And that should squish it vertically. Now this axis shifted as far as visually how far apart it is because I changed my scale. So it's a little bit hard to see, but it should look flatter like this because I compressed it from the top. So that's my transform tangent function, and it keeps repeating to the right and to the left. So you have asymptotes the same distance apart going on forever to the right or left, but one period is enough to know that we've got the idea. All right, move to another blank page and let's do cotangent. So as always, we'll start with the simple parent function. So cotangent of x. So cotangent is the reciprocal of tangent. So that's going to be related and similar, but it's not a, well, anyway, we're going to dive in and do it. So cotangent also has a period that's equal to pi, and it has the same general shape. But the one cycle of it, if you think of it that way, if I let this be 0, goes between 0 and pi. So the center, if you will, is not in the same place as it was on the tangent function. So we're going to call, actually, I'm not going to call it the center. So I do have a point at pi over 2, 0. And I'm going to have asymptotes at 0 and pi. And it looks similar to tangent. So remember that tangent had this shape, but cotangent is going to twist the other way. So cotangent looks like this. So the twist goes the other direction. So this is my cotangent function. So a lot of these things are the same as tangent. So if I have A cotangent B x minus C, A is a vertical stretch or shrink. Clearly spelled that wrong. Oh, that was okay. the period is going to be the same. So that would be pi over b. C is the horizontal shift. But if we think ourselves as shifting this asymptote, so it starts at an asymptote, right? If we think of 0. So C would give us the left, if you will, asymptote rather than the center. All right. So what does that tell us about the period? So if I do that left asymptote and I add the period, that's going to give us the right asymptote. So let's look at an example. So let's do y equals cotangent 3x plus pi over 6. So my A is 1, so I don't have a vertical stretch or shrink. My B is 3, so my period is pi over 3. C is negative pi over 6, so that would be left, and that's going to be an asymptote. All right, and then where's my other asymptote? So negative pi over 6 plus the period, which is pi over 3. So that would be negative pi over 6 plus 2 pi over 3. 2 pi over 6 common denominator. So that gives us positive pi over 6. So that is where my right asymptote is. So let's get these on here. So if let's say I put my 0 here, and I need multiples of pi over 6. So let me have this be negative pi over 6, 0 pi over 6, 1 pi over 6. And it turns out that that's actually the entire period here. That's a distance of pi over 3. My asymptotes I'm graphing in red. And so I shifted my asymptotes. So my center is always halfway in between those. So here, and I didn't have a vertical stretch or shrink. So I'm going to graph this curve. Remember, it's a cotangent, so it twists the other way from tangent like this. And I'm done with this one, but do remember that it keeps repeating. So I'd have another one here. And I'd have another one over here. And that is cotangent. All right, so we did a cotangent. So now we have to do secant and cosecant. So let's look at secant. Parent graph. So let's look at what y equals secant x looks like. So the period for secant is 2 pi, much like sine and cosine, because secant is the reciprocal of sine. And it has a center. Show you what that means when we get to the graph at x equals 0. So first we're going to graph it. So secant has asymptotes at negative pi over 2. Let's see, I'm going to put my 0 here. and positive pi over 2. And then they keep repeating, and I didn't cover an entire period here. That's only half of a period. So if I mark off pi and 3 pi over 2, I have asymptotes every horizontal distance of pi. That's not an entire period. An entire period or an entire cycle goes from negative pi over 2 to positive 3 pi over 2. So this is one full period. And notice that's a distance of 2 pi. And I also have, I'm going to call them, sorry for the puppy playing with the squeaky toy noises in the background. So I also have these peaks and valleys, which will show up when I start doing it. So on the parent function, a vertical distance of 1 and -1 is going to be important. And I'm going to have, they're not asymptotes, but they're boundaries here at +1 and -1. So I'm going to mark those off so I can keep track of that. So what my secant function looks like. So between negative pi over 2 and positive pi over 2, we get this curve that's above my horizontal line at y equals 1, centered at 0, 1. And it looks like this, like a U, if you will. And it does not cross these vertical asymptotes, but it touches 1 here. And then between pi over 2 and 3 pi over 2, I get a curve that's below -1, so centered at pi and facing down like this. So we'll call this one full cycle, and then it keeps repeating. So I get above here, and if I keep going to this direction, they alternate below. And then I would get above, but I've only got enough room to do half of it. It looks like that. Remember, this is one full period. All right, so let's write down the information here. So the center at x equals 0 here is, I'm going to call this a peak, even though it's clearly a valley, right? So like these curves, it has a boundary here at 1, and this one has a boundary at -1. I'm going to call that a peak. I've got to call it something. So if I have a transformation on my secant function, so it could look like a secant bx minus c, and we're not doing the vertical transformations here. So the period is 2 pi over b, much like cosine. But remember, that gives us the top and the bottom curve in that one period. So for A, it could be a reflection if it's negative, or a vertical stretch or shrink. Nope, I take that back. Sorry, I was thinking of tangent. Could be a reflection, or it actually moves this peak. So it moves the peak, which is not a math word really, up, down. Okay, I'll show you when we do this. C, like always, is a horizontal shift. So asymptotes. So C moves this center point. So if I shifted the center point, my asymptotes are still centered around that. So if I do my C, that's my shift. And then I do plus or minus, but remember, this is only half of a period between the asymptotes. The full period gets me 2 sets of asymptotes, if you will. So the distance from the center to an asymptote is actually 1/4 of the period. So the period over 4, and then it repeats. All right, so I'm ready to do an example. So here we go. Y equals 1/2 secant 2x minus pi over 6. So A is a half. There's no reflection because it's positive. And the peaks are not at +1 and -1, but they're at +1/2 and -1/2. So that's my horizontal boundaries. They're not asymptotes because they're not approaching. The period is 2 pi over b, so that would be 2 pi over 2. So the period for this transformed function is pi. And then I'm going to end up needing my period over 4 to find my asymptote. So that's going to be pi over 4. All right. So C is positive pi over 6. So that would be moved to the right. And then ultimately, I'm going to need to add and subtract pi over 4. So pi over 6 plus pi over 4 is pi over 12. 2 pi over 12 plus 3 pi over 12, which is 5 pi over 12. And then pi over 6 minus pi over 4. And if you do the common denominator and work it out, it turns out to be negative pi over 12. And then it repeats, but let's start our graph. So I want to put my asymptotes in the place where they belong. Actually, you know what? I do want to find that other asymptote. I'm going to do it down here because I ran out. So then I have another one of distance of half the period from here. So also another asymptote at 5 pi over 12 plus half the period, which is pi over 2. So that would be 5 pi over 12 plus 6 pi over 12. So that would be 11 pi over 12. Okay, I'm ready to label my axis. So I'm going to do it in multiples of pi over 12. I'm going to put my 0 somewhere. So I'm going to put it here. And I'm going to leave every halfway between my dark marks as pi over 12. So pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, 6 pi over 12. I'll label that up here because it's hard to see. 7 pi over 12, 8 pi over 12, I'm off a little bit. Oh, I missed one. This was 7 pi over 12. My apologies. This is 8 pi over 12. And this is 9 pi over 12. And this is 10 pi over 12. And then this is 11 pi over 12. All right. So I know that I have asymptotes at negative pi over 12. And I have one at 5 pi over 12. And I have another one at 11 pi over 12. My scale must be off. Oh, it is. Apologies. I should have started at negative pi over 12, which I didn't mark on here. Good. All right, so those are those asymptotes. Now, my peaks and valleys happen at -1/2 and +1/2. So I'm going to be consistent with my labeling here. And this is -1/2 and this is +1/2. So I have those as boundaries as well. All right, now I'm ready to graph. So remember, this was shifted and my first region has a curve that goes up and it's centered. So halfway between -π/12 and 5π/12 is at π/6. And that peak, even though it's a bottom, is at π/6. And my curve goes like this, approaches the asymptotes. And then in this region, I have the one that goes below. So that peak is at -1/2 and it goes down like this. And I'm done, but remember it does repeat. So I'd have one above here and I'd have one that was below here. It would be centered, let's see. It would be centered here. So it would look like that. So that's it for secant. One more, now we're going to do cosecant. Parent graph, y equals cosecant x. Very similar to secant. It's a reciprocal of sine. Wait a minute. Oh yeah, I'm doing cosecant. Okay, so cosecant is the next one. So we're doing cosecant. So the period of cosecant is 2π. It has a center at x equals 0, which is not a middle of a curve, it is an asymptote. So I'm going to start putting these things on the graph. So if I put my 0 here, and I label every π/2, π/2, pi, -π/2, -π, and I put my asymptotes in. So at 0, I actually have an asymptote. And then my period's 2π, but I have asymptotes every half a period. So I get one there and one here. And just like with the cosine, secant, I mean, I have these peaks, if you will, at the a value, so plus and minus 1. But my period, my one full cycle here is going to go between -π and +π. So this is one full cycle, which is a period, 2π. So how is it different than secant? My curve on the right here is above, so to the right of 0, and my curve on the left is below. And then of course it keeps repeating. So I have below over here and then above over here, and it keeps going forever to the left and right, but one full period is between -π and +π. So here's the other information that we need about cosecant. So if I have a transformation, it's A cosecant B x minus c, and we're not doing vertical transformations. So the period is equal to 2π/b. A moves the peaks. C is a horizontal shift. Asymptotes, because I'm starting at 0 at an asymptote, so the asymptotes are going to be at C plus or minus half the period. And that gives me my my middle asymptote, my left asymptote, my right asymptote, and that's the whole thing. So here's our one example of this. So y equals 3/2 cosecant 1/2 times x minus pi over 4. So A is 3/2, no reflection. And the peaks are going to be at plus and minus 3.5, which is 1.5. The period is equal to 2 pi divided by 1/2, so 4 pi. C is positive pi over 4, so that's right. And remember, that's an asymptote. So I also have more asymptotes. So also at that shift, so pi over 4 plus 2 pi. So that works out to be 9 pi over 4. And I have one at pi over 4 minus 2 pi. So that happens to be at -7 pi over 4. And now I'm ready to graph. So I need to label my axes so they work. And I've got things in multiples of pi over 4. So I'm going to put pi over 4 here. I'm going to count by pi over 4s. Actually, I'm going to count by every other pi over 4. So this will be 3 pi over 4, 5 pi over 4, 7 pi over 4, and 9 pi over 4. And now I'm going to do negative pi over 4. So if we're interested, 0 is there. Negative 3 pi over 4, negative 5 pi over 4, and negative 7 pi over 4. So I'll put my asymptotes on here. So notice I had one at -7 pi over 4, so that's here. I have one at pi over 4, which is here, and another one at 9 pi over 4. And then if I label these the same way I have been, 1, -1, I have these peaks at 1.5 and at -1.5. And now I'm ready to graph. So my curve to the right of my transformation is above, and it's centered halfway between pi over 4 and 9 pi over 4. So here, and it hits the peak and it's above. And then I have one below to the left, centered between these asymptotes. So at -3 pi over 4, and it goes below. And we're done with cosecant.